So I wanted to start off this chapter 2 review by going over constitutional isomers, and after that we're just going to go into the review questions, right? So for instance, I want you to draw out as many structural isomers as you can for C6H14. The first thing you want to do is realize that this is going to be an acyclic formula. The difference between cyclic and acyclic is that acyclic is going to have N and H will be what? It would be 2N. So that means that we're going to be acyclic, right? So plus 2. So we have C6H 2 times 6 plus 2. So that would be C6H12 plus 2, which would be C6H14. But why does that matter? Well, it matters because cyclic is going to be CnH2n, meaning that this formula would be C6H12. That would be cyclic, and this is acyclic. Well, this means that we would have like rings or pentagons or whatever, those weird looking things, right? And acyclic means that we're just going to have lines going up, down, sideways, whatever. There's just lines. So realize that this would be your formula for lines, and this is your formula for like triangles, pentagons, octagons, centagons, right? For this one, we would be working with only lines, right? All right. So again, C6H14. We're going to draw some isomers, right? The first thing I do is that I draw out just the 6 bonds, right? So 1, 2, 3, 4, 5, and 6. This is going to be our parent chain. The next thing I want to do is label it and go on to decreasing carbons. So now I'm only going to do 5 carbons. 1, 2, 3, 4, and 5. Okay? And notice that I have one more carbon to put on. If I put on that carbon right here, it's going to be the same thing as this one. So they are not constitutional isomers. However, if I put one right here, then it is a constitutional isomer. There are still 6 carbons, right? But they are plugged in differently. So let us do it again. 1, 2, 3, 4, 5. Now I cannot use this carbon because it would be the same thing as this one. Okay. Well, what about this one? Well, yeah, because this is not the same as that one, and we still have 6 carbons. Okay. Well, let's go to 5 again. Can we do it again? 1, 2, 3, 4, 5. All right. I can't use this one because I just used it, and I cannot use this one because I just used it. If I do this one again, it's going to be the same one as 6. This is just the same thing as flipping it this way, right? So if you were to twist it around like that, it would be the same thing as 6. So we cannot use 5 anymore. Same thing, this would be the same as this. We just twisted it around, like right there, right? So number 5 is not good. Let's go on to 4. Let's do 4. So 4, you just go down the line, just keep doing it. 1, 2, 3, and 4, right? And now we need to put on 2 more carbons. So we cannot use this one because that would be 5. So 5 and 6. That's good. 4 again. And 1, 2, 3, 4. Let's do this. Can we do the same thing here? Right? Can we do that? Well, no, because you could just flip this upside down and then twist it to the right, and it's the same thing as this isomer, or this molecule. So what can we do? Well, we could do something tricky. We can do this. We can put one right here and the other one right there. Right? So let's see, 1, 2, 3, 4, 5, and 6 carbons. Put your bonds somewhere else, right? Try to get as many constitutional isomers as you can. We can no longer work with 4 anymore, because if we kept doing this, we would just have repetitions. That's 5. This would be 6, right? Well, yeah, it would be the same thing as this one. So we can no longer work with 4. And now we go on to the third one. 3 usually tends to be the hardest. 1, 2, and 3. So let's work with this. We do 1, 2, and maybe branch that out, right? So you can no longer do that anymore, because if you try to do it again, it would be that, and it's like the same thing as this, right? You just rotated it. Not good. So just start with your parent and then decrease the number of bonds you have, and just put those bonds that you decreased onto different portions of the molecule, right? And make sure that you don't have any mirror images or any copies, all right? I think that's about it that we can do for this problem. For this problem, we have to identify which molecule has no dipole moment, right? So a dipole moment is when an atom is connected to another atom that tends to be more electronegative, and it experiences like a tug, like a magnet from that electronegative atom, right? So the force that this carbon experiences goes this way towards the oxygen, and it's so strong that this force actually pulls a lot of the electrons off the carbon. And so that is a dipole moment, and it's given by this arrow, and that arrow points towards more electronegative atom. All right, so knowing this, electronegativity, as we know, goes towards fluorine horizontally and diagonally, right? So fluorine is said to be the most electronegative. So no matter what, fluorine is going to be super electronegative, especially when compared to carbons. So let's do this, right? We're going to kind of blow up this image. This carbon is connected to a fluorine, and it's connected to another carbon that's connected to a fluorine. Right, so the fluorine has such a strong electronegativity that our dipole moment is going to go this way, and it's also going to go this way. Notice that they both point towards the left, or the right, excuse me, and so we can actually add up the vectors, or, I mean, that's kind of like a mathematical way, but we're just going to make a triangle or a square. So that goes there, that goes there. We're going to connect these, and well, how can I say this? It's like that one goes there, that one goes there, and so the resultant is going to be like over here, right? Because we're going to make like a parallelogram or whatever, right? Just complete the triangle. Goes this way. So we have a net dipole moment going that way. Or just say it's going to the right. Don't overcomplicate it. For this one, our dipole moment is going this way. It's going that way. If we complete it by making this square, we have a net dipole moment that goes directly up. And that's true. If you have a piece of paper and you kind of bend it, so it's like that's your piece of paper, and then your fingers pull this way and your fingers pull that way, the paper is going to go up, right? Cool. And our dipole moment over here is only to the right, so our moment is going to go towards the right. We have a dipole moment. Over here, we're directly across from each other. We have a dipole moment right here and a dipole moment right there. To make this more obvious, it's like saying this, right? I should say. It's like you're playing tug of war and you're playing with your clone. So your clone has the same amount of strength as you do, so that rope doesn't budge, it just stays in the middle. So these effectively actually cancel out. since they're in the same direction. They're pointing this way and they're pointing that way, right? These are technically pointing at different directions and different angles, so they don't cancel out. In fact, they actually help each other. These ones, they hurt each other and they cancel out. So it'd be A, or it would be this one that does not experience a dipole moment. Right. So which one of these molecules do not have a dipole moment? So which one has 0 dipole moment? Okay. First, I like doing kind of like the simplest one first. I like doing C, which has a hydrogen and 3 chlorines. Right? So chlorine is actually more electronegative than carbon, so we're going to have a dipole moment right there and a dipole moment right here, also a dipole moment over here. We're going to ignore hydrogen. It's like the weakest one, right? It's less electronegative than carbon. So notice that these dipole moments cancel out, the ones across, but hydrogen is so weak compared to chlorine that effectively the dipole moment goes completely towards the right. So we do have a moment, right? So this is not good. Okay, let's do carbon monoxide. So carbon and oxygen. Carbon is less electronegative than oxygen, so we have a dipole moment that goes to the right. Okay, it is down to carbon dioxide and sulfur dioxide. Let's do sulfur dioxide. We have an oxygen connected to a sulfur connected to an oxygen. There are 6 valence electrons per sulfur and per oxygen, so effectively it's like 6 times 3, which is 18, right? So we already use 4 electrons, so 18 minus 4 is 12. And typically oxygen wants to have 2 bonds, right? Oxygen wants to have 2 bonds, right? So let's do this. 2, 4, 6, 8. So now we have 10 valence, we have 10 electrons to work with. 2, 4, 6, 8. And we could put a lone pair on sulfur because sulfur can expand its octet. It doesn't obey the octet rule, right? Okay. And again, yeah, you could put a bond right here and a bond right there, but oxygen is really, 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 really happy with 2 bonds, all right? So as often as possible, try to make it neutral. Try to make it, have 2 bonds. And yeah, let's see, 6 minus 2 is 4, and then 4 minus 2, 4 bonds is neutral. So overall, this is like the best structure, right? Sulfur is neutral. 6 minus 2 electrons is 4, and 4 minus 4 bonds is 0. The same thing for oxygen. So this is a really good structure. But notice that, let's see here. Sulfur is more electronegative than oxygen, right? So you would think that this cancels out because they're completely across from each other, and you would think that they would cancel out, right? But that's not true, because the electrons actually generate a dipole moment themselves, right? Kind of like they bend the molecule. They bend the molecule, and essentially they make it so that our moment goes completely upwards. So it's like the same thing for water, right? You see this a lot in the water molecule, that we have a dipole moment going completely up, right? So this has a moment, which is not good. This leaves us with carbon dioxide. All right, so let's draw out carbon dioxide over here. So here is carbon, here is oxygen. Oxygen loves to have 2 bonds, carbon loves to have 4 bonds, right? And notice that our dipole moment goes over here and over there. And these cancel out too, completely. So there is no dipole moment, meaning that we are not polar. So this is the best one because we don't have any dipole moments bending us or twisting us, right? It completely cancels itself out because it's on the opposite ends of each other. So what functional group is present in this molecule? Whenever you see just carbons, right, just carbons, and you see either chlorine, bromine, or iodine, you're gonna instinctively know that it has to be an alkyl halide, right? So yeah, it's an alkyl halide because it's completely attached to a carbon. Here's a blow-up image of what you see here. So here's a carbon, here's another carbon going towards you, and then there's a bromine going back into the screen. Alright, so we figured out that it was an alkyl halide, but is it a primary, secondary, or tertiary alkyl halide? Well, the way you can tell is that you would have to kind of look at the carbon that it's attached to. So again, let's make up a blow-up image. Here's a carbon, there's another carbon, and that carbon has a bromine. We're just going to simplify it. Alright, so this bromine is attached to one carbon, but that carbon is linked to 1 and 2 carbons. Okay? This can also be an alcohol, right? So we would have the same thing if we had a carbon, and a carbon, and then an alcohol. If it's attached to a carbon, and that carbon is attached to another one, or another one, then it would be what? In this case, it's a secondary. If we had, yeah, we could do this. If we had, what? A hydrogen or a carbon right here, then it would be what? A tertiary, because we're attached to 1, 2, and 3 carbons. If this were a hydrogen, we would be a secondary, because we don't count hydrogens or anything else. We only care about carbons that we're touching. So if this carbon is touching another carbon, it would be a primary. If it's touching 2 carbons, then it's secondary. If it's touching 2 carbons and a hydrogen or whatever, then it's still secondary. Okay? Notice that this is completely different for amines, right? Amines are different. For instance, if you were to have a carbon bonded with another carbon with a carbon, and then we have an amide group, or an amine group, excuse me, then what? Well, we're only attached to 1 carbon. It doesn't matter that this carbon is attached to that one and that one. It's the one that nitrogen is touching. You can think of the N in nitrogen as next to. Yeah, this nitrogen is next to 1 carbon. If we had our nitrogen group attached to some carbons, then what? Well, it would be next to 1, 2, and 3 carbons. We don't care about hydrogen, alright? Because a hydrogen is hiding. So it's next to 3 carbons, so this would be a tertiary amine. And likewise, since this is only next to 1 carbon that is next to 2 carbons, right? It would be a secondary alkyl halide. Right. So just mainly remember this rule for carbons and bromines or whatever, and then remember the different rule for amides and amines, right? So amines only care about the carbon they're next to, and then bromine, alcohol, whatever, cares about the carbons that the carbon is touching. So the mother carbon has 2 children carbons. That's one way to think of it. Which one of these molecules has a tertiary carbon? So which carbon is attached to 3 other carbons? Well, this one is attached, so this carbon is attached to this carbon, right? That makes it a what? Primary carbon. And that carbon is attached to this carbon and that carbon, so that makes it a secondary carbon. Alright, what about this one? Well, we are attached to 1 carbon, 2 carbons, and 3 carbons. It doesn't matter that we're also attached to a fluorine, because that fluorine is not a carbon. and so we don't really care about it. And hence, this carbon right here is attached to 3 other ones, so this is a tertiary carbon. Alright, let's do this one. This is only attached to this one, so it is a primary carbon. And this carbon is attached to 1, 2, 3, and 4. So that's a quaternary carbon. Not what we're looking for. This is the same as this one and that one, so we're not going to do that one. This carbon is attached to 1, 2, and this carbon is attached to 1 and 2. So that's not good either. And this carbon is only attached to that one, so it's a primary carbon. Not good. Okay, well this carbon is attached to 1, and this carbon is the same thing. This carbon is attached to this and this one, so it's a secondary carbon. In fact, they're all secondary right here. Not good. This carbon is attached to 1 carbon, primary. This carbon is attached to 1, 2, and 3. Cool. So that's a tertiary carbon. So we did that. And that's the same thing, 1 carbon. So 1, 2, and let's see. 1, 2, oh, 3, sorry. So yes, this carbon is attached to 1, 2, and 3 right there. Okay, and this carbon is only attached to 1 and 2. If, in case you're kind of confused, we have a carbon attached to another carbon attached to a carbon with a bromine. And then we have carbon, 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 carbon. Okay. This is a primary carbon. This is a secondary carbon. This is also a secondary carbon. And this is the primary carbon. You should be able to do that on the test, right? Which one of these molecules contains a secondary alcohol? If this kind of frightens you, just think of the line structure. So we have a carbon, a carbon, a carbon, and another carbon with an alcohol. So just ignore the H's between the carbons. Alright, well, like I said, this oxygen is attached to the mother carbon, and that mother carbon is directly attached to her children. So she has 1 child and another child. So she has 2 children in total, okay? And that means that we are a secondary alcohol. Right? Okay. So let's transform this. Carbon, another one, an OH, and that. So this alcohol group is attached to the mother carbon, and that mother carbon is directly attached to her child. She only has 1 child, so that is only a primary alcohol. Okay. Let's go over here. Just do the kind of line structure or condensed formula. Carbon, another one, and another one. Alcohol. That alcohol is attached to the mother carbon, and that mother carbon has 1 child, another child, and another child. She has 3 children, so that is a tertiary alcohol. Alright, so we were looking for a secondary alcohol. It turns out to be this one. Alright, which functional groups are present in this molecule? Instinctively, we could say that, oh, there's an alcohol, right? So this is completely an alcohol, and the question is asking us to be really specific. Let's blow up this image. We have a carbon attached to another carbon. That's 1, right? And that's kind of weird. Yeah, so let's just do this. 1, we have an alcohol right here. So that alcohol is attached to the mother carbon. That mother carbon has 1, 2 children. That means it's a secondary alcohol, right? It is a secondary alcohol. And that's about it, but then you almost forget about the alkyne. Alkyne. Another way to remember this is alkyne 3 of a kind, right? So 1, 2, and 3. And then an alkene would be king and queen, king and queen. So king and queen, or queen and king, whatever, right? Those are the easy ways to kind of remember your functional groups. Also, an arene, if I can draw one, they kind of look like an arena, right? So an arene is arena. Ugh. Yeah, it's an arena, where the little electrons of carbons fight to the death, and there's lines everywhere, right? So an arene kind of looks like an arena, aromatic or whatever. So yeah, it would be a secondary alcohol with an alkene attached to it, or alkyne, three of a kind. All right, so which functional groups are present, and are they primary, secondary, or tertiary? Well, all right. Notice that we have an alcohol, and that alcohol is attached to a carbon, a carbon that has two children. So we have a secondary alcohol. We also have a halide, right? That's a halogen. Halogens are chlorine, bromine, and iodine, and also fluorine, if you want to be more specific. So those are halogens. That's an alkyl halide. Alkyl halide. But is it primary, secondary, tertiary, or what is it? Well, it's attached to this carbon directly, and that carbon, it has one kid, it has one child, so we could say it's a primary alkyl halide, right? And yeah, that correlates to answer choice D, right? Cool. So what you learn from this is that alkyl halides kind of they behave the same way as alcohols. The only thing that differs when you're doing this method would be amines or amides. So there aren't any amines or amides, so we could just count normally like we've been doing so far. Which one of these molecules contains a tertiary amine? Right off the bat, we can eliminate this one because this functional group is an amide or an amide. You could tell by this nitrogen having an oxygen is bonded directly to a carbon that has a double bond to oxygen. So an amide or an amide has a seed. This oxygen looks like a seed, so that amide has a seed, right? Really helpful, so we can eliminate that one. We're looking for a tertiary amine. It does not mean that we are connected to a carbon that has 3 bonds, right? That's not correct. So this one, that's a carbon. That's what we're touching, and that carbon is touching 3 other ones. But we don't do that for amines. We only care about the one that's next to N. That's what N stands for. N stands for next to. So we are next to one carbon, right? So this would be a primary amine. And so we can eliminate this one. Okay. So this one is next to one carbon. It's a primary amine. Not good. What about this one? Well, it's next to 1 and 2 carbons, so that's a secondary amine. Not what we're looking for. Pretty bad, right? So I hope this one is right. Well, let's see. We are next to 1, 2, 3 carbons. Okay, so that's a tertiary amine. The same is true for amines and amides. All right, so amines and amides use the same thing. They're different from alcohols or halides in the way that you count them. Which one of these molecules contains a ketone? Well, a ketone consists of a carbon with another carbon and another carbon with a double bond to an oxygen, okay? So that's what a ketone is. If you want to see a line structure, like this, okay? They're typically found in the middle of a molecule, in the middle of a chain. All right, so number 1, what's wrong with this one? First off, it's not a carbon attached to this other one. That's an alcohol, so we already know that this is incorrect. Also, there's a hydrogen right there, so that's bad. if you're stressing out about trying to connect the dots, just ignore the hydrogens and just make a carbon, right? So carbon bonded to another carbon with another one. This one is double bonded to an oxygen. So if we were to ignore this, it's a straight up ketone. Like that's what we're looking for, okay? This is pretty good because it has a carbon on each side right there, and they're attached to the mom, right? So this would be the correct one, right? It's like the same thing as this one. What about this one? We have a carbon with an oxygen and a carbon. This actually is a what? An ester, right? Well, is it? Yeah, it has to be because, well, you have a carbon that's double bonded to another oxygen. So when you're looking for esters, they could be like this: the carbon, oxygen, and then a carbon. So that oxygen has to be bonded to a carbon, and that carbon has to be double bonded to this oxygen to be an ester. Ester, sorry. Yeah. And ester kind of rhymes with Easter. It looks like Easter. And these oxygens kind of look like those eggs that you try to find at the Easter egg hunting, right? And you have to walk across your backyard, and an egg is usually close to another egg. So this oxygen is really close to this other oxygen, and so you would find eggs like that. This could be like your little sidewalk that you would go on, your pavement, okay? So that's another way to remember esters. This one is not a ketone. It has hydrogens on it. Not good, okay? It's really not good. It's actually an aldehyde. So yeah, not good. Formaldehyde, to be honest. So it's bad. This is also bad. Okay, what about this? Well, you need a double bond to be a ketone, and that's actually an alcohol. Not good, okay? Which functional groups are present in this molecule? We can already see that this is an alkene because it's a double bond. But sometimes it's not going to be that easy. Sometimes you're going to have, this kind of ring, right? That has 1, 2, and 3. And you can't just say, oh yeah, these are alkenes. Well, no, because if you have 3 of them, inside a ring, then it's not technically a functional group. It becomes like a benzene or, a phenol or phenyl, depending. But if it's like this, right, and you have like 1 or like 2 of them, then yeah, you can say, oh, alkene. Or even if it's just 1, like over here. But if it's 3 in a ring, then you don't do that. Don't circle it, okay? Okay, cool. Now you'd probably saying, oh, this is alcohol, right? This is incorrect. See, if we make a blow up image, we have carbon. We're going to be blowing this image up right here. Okay, we have a carbon attached to this carbon, attached to this other carbon, right over here. And what they're saying, what you're looking at is like this, right? Oh, that's an alcohol. But what's the problem? 1, 2. You want 4 bonds, but you have 2 bonds on carbon. So how can we remedy this? How can we solve this? We can double bond oxygen. Oxygen likes to have 2 bonds, by the way. And we can just take hydrogen right here. So 1, 2, 3, 4. We have 4 bonds to carbon. And what do you know? Well, look. Oh, this is an aldehyde. Because, well, if you were to take out this hydrogen and put a carbon, you would get a ketone. So ketones are kind of like siblings to aldehydes. And this would be an aldehyde right there. This is the aldehyde family. So when in doubt, if you're confused, just draw up like a blown out image and you'll be fine, okay? So which molecule or which functional groups are in testosterone? whenever you see these, you should instinctively see an alcohol, right? So that's an alcohol, right? We have that. What kind of alcohol is it? Well, it's attached to this carbon that has 2 children, so that's a secondary alcohol. Right? And we also have a ketone because it's just a carbon and another carbon and another one. So that's a ketone. Okay. And this is an alkene. We can do this because there aren't like 2 other double bonds. There's only one. If you have this, you can also do that. You could say, oh, alkenes, but you cannot go, oh, alkenes, right? You can't do that. That's bad. So that's an alkene. Okay. And this would also be what? This would be a ketone again, right? So we have a secondary one, a ketone, and an alkene. Which functional groups are present in this molecule? Right. So for starters, this right here is not a molecule, or that is not a functional group. It's actually just kind of like what you're seeing me draw is, let's see, that is a 1, 2, 3, 4, 5, 6. That's a hexane. And we're actually just laying the hexane down on the floor and kind of like bumping it up, right? So it kind of looks like this. So that would be 1, 2, 3, 4, 5, and 6. If you can see, it's like it's called a chair conformation, and I'll show you how to draw it later. Kind of, they're pretty ugly. So that's really just a hexane. It's not a functional group. This would be a ketone, except we're actually connected to an oxygen. So what is that? You have 2 Easter eggs, that becomes an ester. So after all this, it's just an ester. Okay. Which one of these intermolecular forces are the weakest? So which one is the weakest? Well, this tends to be like the best one. This is the strongest one. It occurs with a metal and a non-metal. Kind of like if you have like sodium and a hydroxide, this is going to be a metal, and it's just going to take all the electrons, right? Or, well, it's not going to take electrons, but it's just going to really be attracted to hydroxide. They don't even touch. They just kind of magnetically attract each other. So that's the best one. Okay. Dispersion. It's very important to know that everything has dispersion forces, okay? This has dispersion forces. CH3 has dispersion forces. CH4 has one. All of them. Anything that you can make has dispersion forces. And so if people have the same thing, then is it really good, right? Like, you might have the newest shoes or something, but if everybody has those shoes, it's not very special, right? And so if everyone has those shoes, then it's pretty weak. Like, your fashion choices are pretty bad. So this is the best one. This is going to be the worst one. This is going to be your answer. That's dispersion forces. Dipole occurs with, well, it's like, it's kind of like when you have carbon and a carbon or something. Yeah, they're both like neutral. I should say neutral. But sometimes the electrons slosh around like a bucket. Like, imagine a bucket full of electrons and you're just kind of like swirling it. The electrons sometimes accumulate over here and they make this negative. Sometimes they accumulate over here and they make that negative. So it's not that good, right? It's like it's not as bad as dispersion, but it's okay. Like, it's not that good. Covalent bonding is what you're known to, like carbon with an oxygen that goes over there. That is secondary, or I should say tertiary, because ionic bonding is pretty good. Hydrogen bonding is the second best, this is third, this is fourth, this is like the worst one. Hydrogen bonding only occurs with nitrogen, oxygen, and fluorine. Okay, so we have to have a hydrogen bonded to an oxygen, so it could like try to H bond with nitrogen or oxygen or fluorine. However, you do not get H bonding if you have what? A CH with a carbon. You don't get that. So this is not going to occur. It has to be attached to either a nitrogen, an oxygen, or a fluorine for it to H bond. Okay? So this is kind of a hard question to do. It's asking which one of these is has the lowest boiling point. Okay. Well, they all have an amine attached to it. So what makes it difficult? Like, how do we solve this? All right, well, we count the carbons. The one with the most carbons typically has a higher boiling point because there's more to boil, right? Let's say if you have to boil a cup of water, that's going to take like 5 minutes. But if you have to boil 5 gallons of water, it's going to take a long time. So the more you have of something, no matter what, the longer it takes to boil. So this has 1, 2, 3, 3 carbons. This is 1, 2, and 3, 1, 2, and 3, 1, 2, and 3, 1, 2, and 3. Well, that doesn't help us, right? Okay, that's pretty bad. But, this also includes hydrogens, right? So notice that this is like, we have 2 hydrogens right here and 2 hydrogens right there. And yeah, we can like put this whole group on this carbon, and that's not going to change a thing, right? We're still going to be bound to 3 carbons. So this is like the exact same thing, except this one would have kind of like, how can I say? This would actually have a higher boiling point than this one. For instance, this is kind of like a ball, right? I'm talking about this one. So it's kind of branching out, you see? And when something branches out, you can easily tear it apart. It's kind of like those piñatas that you see at the Spanish stores, right? The ones that are shaped like stars. You can just grab onto a leg and just break it, right? But it's a lot harder to break something when it's linear. So there's nothing that you could grab a hold of with certainty. And so this one would have a greater boiling point than this one, okay? Because it's going to be a lot harder to break a long chain, right? And you can break a small chain really easily. So this would be out of the question. Let's use a different color. This would be out of the question because it's branching out. All right. Okay. And what else? Well, this one is actually really polar. We have the carbons being attracted to the nitrogen right here as well. So polarity increases boiling point. That's not good. It's really not good for us. Bad. And again, this is kind of like branching out, right? Oh, so this is not good either because this is a long chain. We don't like long chains. And actually, I shouldn't have erased this because this is still in the running. All right, so it's either between this one, or this one. So which one is it? I want to trim as much fat from the molecule as I can, right? So both of these have hydrogens, and those hydrogens kind of weigh me down. Yeah, it's going to take some energy to break those hydrogens down. This one does not have any hydrogens, it just has carbons. So it's the smallest one, it only has carbons, there's no hydrogens in it to weigh me down. So I'm going to boil real quickly, you know? So this one would have to boil super quickly because we don't have any hydrogens, like here. And we're branching out like this. So we have the best of both worlds. So which one of these has the highest boiling point? Whenever you think of thinking of highest boiling point, you always want your molecule to be polar because polarity actually increases boiling point, right? And right off the bat, we notice that we have an alcohol, right? And alcohols actually increase the boiling point. So whenever you see an alcohol, instinctively look at that in good favor, right? So this is really good. This is really good for us because that increases the boiling point. It adds energy to us, so it takes longer for us to break down and when you try to boil us, right? So this is good. This one only has dispersion forces. Let's call that dispersion forces. Technically everything has dispersion forces, but this one only has dispersion forces. This is polar, and this is polar too. As you see, we have an oxygen right there. But there is no H bonding because oxygen is not connected to a hydrogen directly, right? And if you want to see this in like a line formula, we have carbon with another one with an oxygen, carbon, 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 right? Like, there is no oxygen bound to us. So the only thing that actually increases the boiling point would be a alcohol group or hydrogen bonding, okay? So the solid alkane is expected to exhibit the greatest solubility with what solvent? So if you ever seen Mean Girls, right? Mean Girls, they had kind of like cliques in their high school. So they would sit down with the kids who were kind of like them. So you would have the jocks, the nerds, the cheerleaders, the just like kind of groups of people that were similar to each other. And so this problem is kind of like Mean Girls, right? We're trying to find a table that we could sit down and have lunch with. So which group of people are gonna let us sit down with them? So this one, if you notice, is just CHs. It's just a carbohydrate molecule. So this is actually non-polar. Okay, so we have to look for something that is not polar. H2O is a famous one you should know. Is an oxygen, and this there's an oxygen right there, and so we will have a dipole moment going upwards because these little electrons generate kind of like little forces, right? Okay, and if you want to do something really cool, right, it's kind of like a cat. So that actually generates a force that makes it polar. So this is polar, right? This has H bonding that are instinctively makes it polar as well. Okay, this is H bonding as well. We have nitrogen attached to a hydrogen, so that's polar. Again, a hydrogen attached to an oxygen, that's an alcohol group, or you can say it's just H bonding, so that's polar as well. So by process of elimination, this is not polar, and if you want to draw it out, it'd be C with 4 chlorines attached to it. 4 chlorines attached to it. So that would be non-polar, right? We have one going here, there, there, and there. These cancel out completely, and we are left being non-polar, so we can have our lunch with carbon tetrachloride. Alright, so these next couple of problems are actually not on the review packet, but I thought that it would be really important to go over structural isomers, resonance structures, and stereoisomers, specifically cis and trans isomers, right? And I wanted to kind of just determine if each molecule is the same one, or is there like some sort of difference between them, okay? So for this one, what you want to do is you first want to count out your carbons, right? So we have 1, 2, 3, and 4, and 5. So 5 carbons, 1, 2, 3, 4, and 5. Right, so we have the same amount of carbons on each one. And after that, if you're still not certain, you can count out the hydrogens that you have here. So this would have 3 hydrogens, 1, 2, and 3. This would have 1, 2, 3, 1 hydrogen right there, because we want carbon to have 4 bonds. That already has 3 bonds, so adding 1 hydrogen would give you an extra bond. So 1, 2, 3, and 4. Right, 4, and let's see, 1, 2, 3, and 4. And that's 1, 2, 3. Okay, so how many hydrogens are in there? So 3, 6, 7, 8, 9, and 10. So we have 10 hydrogens. Okay, what about this one? This has 1, 2, and 3. This has 1, 2, 3, 4. Okay, so 1, 2, 3, 4. 1, 2, 3, and 4. 1, 2, 3, and 4. So that's 3, 6, 7, 8, 9, 10. So that's also 10 hydrogens. Okay, so that means that we have the same amount of carbons, we also have the same amount of hydrogens, but these look completely different, right? These molecules look completely different. So what's the problem here? Well, the problem here is that you are kind of like to get to this molecule right here, right? They're actually twisting this. If you have a model on you, they're actually twisting this bond upwards. More specifically, they're going kind of like this way, right? And the problem is that you can't do that. You can't rotate on a double bond because this carbon is connected to another carbon. And the way this happens is that with a pi bond, you kind of have like this balloon shaped thing going in the background and making a pi bond. So that's one pi bond. You have kind of like this other one. So imagine like you have a hamburger and this right here is going to be the lettuce, right? So this is your bun, this is a pi bond, and your lettuce is going to be like the sigma bond. So whenever you try to twist it, it's like someone gets the hamburger and just twists it, right? Your hamburger is going to be shattered. And do you want that hamburger? No, you don't. So you don't twist hamburgers. You don't twist pi bonds. If you have a physical pie, you're not going to actually twist that pie because the apple is going to go all over the place. And so you can't twist pi bonds. The energy required to twist a pi bond is so great. It would be like kilojoules, right? Per mole. And it's not favorable. It takes a lot of energy to break it, and nature is pretty lazy, so it doesn't like to do a lot of heavy work when it comes down to breaking pi bonds. So this is not good. This because they have the same carbons and hydrogens, they would actually be classified as structural isomers because you have to like connect it differently to get this sort of structure. Okay, so they are structural isomers because you can't twist around double bonds, okay? So you cannot twist around double bonds. That is very important for you to know, right? So they are structural isomers because they have the same formula, but they are connected differently. Or I should say before we leave that question, yeah, they're like structural isomers, but a specific type of isomer that they are is that they are actually stereo isomers. So this is cis and trans, right? So for instance, this is like, we could say that this is down, and this would be up. This is an up conformation relative to this carbon. So let's see, to this carbon. So this carbon, this group is downwards, and this one is upwards. So it depends on what you want to say. You can say that this is like cis, and this would be like trans, because we actually we traveled upwards. So yeah, there would be stereoisomers. Okay, so yeah, like stereoisomer is kind of like a subgroup of structural isomers, but stereoisomers have to deal with locations. Okay, so this would be a cis-trans isomer. More importantly, it would be a distereomer. Okay, but you'll learn more about that later. So more specifically, this would be a distereomer. All right. So which one is this? Is this the same compound, a structural isomer, a resonance, or a stereoisomer? All right. Well, we count out our carbons. So 1, 2, 3, and 4. 1, 2, 3, and 4 with 5. 4, 5, 3, 4, 5. Sorry. Let's just do that, right? So that's also 5. So they have the same amount of carbons right here. So what do? If they have the same amount of carbons, you just go to hydrogens, okay? So this would be 3 hydrogens. This would be hydrogen, two of them, and 3 of them. This would have 2 hydrogens, H, H2, and H3. All right, so what's different? So these two did not change, okay? That one stayed the same. This one stayed the same too. and that one too. But we have an H3 and we have an H2. So that is structurally different. Do they have the same amount of hydrogens? Let's see. 3, 4, 5, 6, 7, 8, 9, and 10. This is 10 hydrogens. This is 2, 4, 6, 7, 8, 9, and 10. That's also 10 hydrogens. So they have the same amount of carbons and hydrogens, but this one changed. So that must mean that this is a structural isomer. It's not a stereoisomer, okay? Because it would be a stereoisomer again if one of these bonds, right? If one of these bonds actually kind of flipped, right? More specifically, if this occurred. So let's do that, right? And notice that we can't do that because of the double bond, so that would actually be a stereoisomer, more importantly a cis and trans isomer. So we're still in the same direction relative to this carbon. We are upwards, we're going upwards like a mountain. So yeah, right? So this carbon, we're still going upwards, okay? Cool. So this would still be a structural isomer since they have the same amount of hydrogens, carbons, and they're not traveling up or down. They're staying in the same plane, right? So this is up and this is also up. So they're not changing locations. All right. Are these molecules structural the same, the stereoisomers, or are they resonant? Well, a really good tip to do is to count out your carbons and then your hydrogens, but let's just see if they have the same amount of carbons, right? 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. They have 5 carbons each. And notice that we have some charges. So whenever you have charges, that kind of hints that there might be some resonance. A quick way to do this, to confirm, is to move your plus or minus charge, depending on which one you have. In this case, we have a plus charge. We're going to move it 2 atoms, right? So this does not count because that's our starting point. So we go 1 and 2. So our plus charge should be over there, and it is, okay? So once we're over here, this double bond should move back 1, right? It should go only 1 molecule or 1 atom backwards, and it happens over here. So that's a really quick way to determine if your molecule or a group of molecules has resonance structures, and indeed this does have some resonance. Or what about these? What kind of molecules are they? Well, it turns out to be the same. They're the same ones. We can get this this group right here and twist it so it becomes this one right here. And we can do this because there are no double bonds. It's only single bonds, and you can actually twist and turn single bonds as much as you want, okay? So it's only with double bonds that you can't twist or turn. With single bonds, you can rotate freely, and you'll be fine with that. We have the same amount of carbons too, right? We have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. We have the same amount of carbons, same amount of hydrogens. We just kind of twisted it. So they're the same one. Right. What about these structures? What kind of structures are they? You're probably thinking, oh, resonance, right? Well, let's find out. Resonance. Well, yeah, I can see how it is, how you could think it's resonance. You could go 1 and 2, and you have your little negative charge right there, and you say it's resonance. Well, you forgot something really crucial, right? You're supposed to move the bond, the double bond, right? In this structure right here, you didn't move the double bond. So how does that impact us? Well, you have, let's see, 1, 2, 3 bonds, so that's a hydrogen. That's a hydrogen 2, right there. 2 hydrogens right there. This is, whenever you have a carbon with a plus charge, it's actually going to be kind of electrophilic, so it's only going to have 3 hydrogens, so it's okay like that. And H3. H3 is the same. This is 1, 2, 3. This is also H. This one right here would actually need a hydrogen. Okay? This has H2, and this has an H right here. 1, 2, 3, 4. So notice, this stays the same, this stayed the same. This one lost a hydrogen, okay? This one stayed the same. This one gained a hydrogen somehow. And that's not really good. That's not really good. They're not resonance because you have these hydrogens popping out of nowhere. You can't really describe how they came out. And we're not traveling anywhere, right? We don't see any bonds traveling or anything out of the ordinary. So they're not stereoisomers. It's not resonance. They're not the same. So the only thing that they could be is structural or constitutional, right? So if you want to use that little trick, you got to make sure to move that double bond. If you see something that used that trick, kind of, and they didn't move that bond, then you cannot say that it's resonance, okay? And now for the final question for stereochemistry, what kind of molecules are they? Well, notice that Br and Br in this molecule are in the same direction. They're coming straight at you. And both the hydrogens are going backwards into the screen. So whenever two of the same atoms are in the same direction, we call that as cis, right? They're the same. But notice that this bromine and this other bromine are in opposite directions, right? We have a wedge for bromine, that means it's coming right at you, and then we have one that's going backwards. And so one is going upwards and the other one is going backwards. They are actually in different locations. We could say that they are trans, and that is a part of a stereochemistry. They are stereoisomers, okay? More importantly, if you need to know this, they are diastereomers, right? So it would be a stereomers. But that's like chapter 4, I think. We will now be doing SP characters, right? So SP characters are pretty simple. Let's say we have SP. How much character is the S? Well, there are only two things, right? So out of those two things, S is 50% of that one thing. So S is 50%, and P would have to be 50%, right? Because 1 and 2, half of 2 is 1, right? We have 1 and 1. So half of 2 would be S. So S is 50%, P is 50%. For SP2, we now have three things. So it could be S, P, and P. S would be what? 33%. Let's do that. S would be 33%, and P would be the rest of 66%. For SP3, we now have SP, right? So we have four things. S would be 25%, and P would be 75%, right? Typically, the more S character you have, the more acidic you'll be. The more P character you have, the least acidic you'll be. So S would be like super acidic. That's what it stands for, like Superman. S, super. So the more S character you have, the more acidic you become. All right. So now we're going to be doing one arrow pushing mechanism problem. Right. So with arrow pushing mechanism problems, you're going to have to actually show where your electrons go and how they got there. Right. So we're not going to be moving atoms, we're going to be focusing on electrons. And since we're going to be focusing on electrons, we should actually put our electrons on our atoms, right? So when I do these types of problems, I like to put my electrons right here. So I know that carbon is going to have 4 electrons. Bromine will have 6, right? Because that bond has 2 electrons, so 2, 4, 6, and 8. Almost all the atoms want to have 8 electrons. This hydroxyl, or I should say this hydroxide, is negative, so we have 2, 4, 6 things around oxygen, okay? And this oxygen will have what? It will have 2 right there. So it got kind of positive, right? It's actually neutral. And right here, we actually got more negative. So we have that. And bromine stayed the same. Poor old bromine stayed the same. Okay, so if something stays the same, like I just said bromine, right? we're just going to ignore it. So imagine that bromine isn't even there because we didn't mess with it, okay? Somehow, oxygen became more positive. And notice that this this hydroxide kind of moved to this carbon, but we're not going to draw it like that yet. We're not going to draw it like that. Okay, well, I mean, we could. We are not going to draw the arrow going over here, right? That's bad because carbon doesn't have any electrons to give. Right now it has 4 bonds and it's pretty content about what it's doing, so it doesn't have any electrons to give out, right? On the other hand, oxygen really wants to bond with something, to become more positive. So it sees an opening right here. We're going to have to try to describe what happened here. So what happened here was oxygen donated some of its electrons, right? If it donates an electron, you can classify it as a nucleophile, right? And so in this case, carbon is acting kind of like an electrophile, kind of. So now we have a problem. We have a problem right here. We have an oxygen, right? And we have a carbon bonding with an oxygen with a hydrogen right there. Do you see the problem? The problem is that carbon now has 5 bonds. It has 1, 2, 3, 4, and 5. That's pretty bad. How can we change that? How can we alleviate it? Well, whenever carbon gets 5 bonds, it has to shoot one out, right? And you can think of oxygen right here as having like a big magnet that whenever carbon shoots out those extra electrons, oxygen just grabs it because it's electronegative. It's more attracted to electrons. And so carbon is going to shoot out this electron, and then oxygen is going to catch it like a pitcher in baseball, okay? And so we will end up getting exactly what we have here. See, we catched these extra electrons right there, and we are more negative as a result. And carbon still remains with its 4 bonds, okay? And of course, bromine does not change, so we leave bromine alone. I really hope that this helps you. I hope that you do well on your exam and that you continue to believe in yourself and that you actually can do really well on this exam. I believe in you. You study a lot and you'll do amazing, okay? So just keep your nose in the books, right? And just believe in yourself. You'll be amazing, and I hope that this made you happy. I hope this actually helped you, all right? So thank you again for watching. It was really fun doing this, and I'm glad to have helped you in any way, okay? Just remember your functional groups, your arrow pushing mechanisms, your stereochemistry, and you'll be fine, right? Anyways, thank you.